Yeah, hello everyone. Yeah, today I'm trying to solve some AMC12B 2021 fall session test. And yeah, because I feel some the problem are really interesting. So I will solve the last 6 problems for today. And yeah, and if you can comment, have any comment on my solutions or have some suggestions, just feel free to leave comments to me. Yeah, this problem are very interesting. So I will solve the 19, 20, 21 as one video, then next two as another video, and last two as third videos. Okay, so now let's start. So the problem is we have a regular polygon with 5, 6, 7, and 8 sides are inscribed in the same circle, and no two of them share the same vertices. And no three sides intersect a common point. So how many points inside the circle can we get? Okay. So yeah, I mean 5, 6, 7, right? I mean if this question if you draw too many sides, it will be very messy, right? So the way we want to do it, we want to construct a systematic way. We want to see what's going on here, right? Okay, so now let's first draw the regular pentagon, right? That's the 5 sides. Okay, let's see the relationship between the 5, 6, 7, 8. Okay, so let's say this is the A1, then A2, A3, A4, and A5. Okay, so let's roughly calculating what is the angle here, right? So I'd like to see, I mean, basically 360 over 5 is 72, 360 over 6 is 60 degrees, 360 over 7 is something 51 point something, like 4 something, and 360 over 8 is 45 degrees. Okay, so we roughly know the relationship between them. Now I can connect, let me connect A1, A2, right? And let's see the 6, right? So basically, we can see the iterative way like this, okay? We can see if we have the numbers, if we have the hexagon, right? For example, this is a hexagon. We call it a B1, B2, right? Up to B6. So I want to analyze to see, okay, so what is the how many the B1, B2, right? Can so on and so forth can interact with AI and AI plus one, right? Okay, something like this, right? And then if we're adding another one like C1, C2, right? For example, C1, C2, then C1, C2, that's the heptagon, right? This is the hexagon. This is the heptagon. I can see what is the how many intersection between C1, C2 and AI plus 1 and also BI plus 1, right? I can see them separately, right? Because if C1, C2 have the pentagon has an intersection, we count by counting this one, then we counting this one adding together, right? The last one is octagon, right? That's D1, D2, right? We want to see, I'm sorry, it's basically it's II plus 1, right? We can see with AI plus 1, BI plus 1, and CI plus 1, right? So we can such systematically counting this problem, okay? So let's see, B1, B2 hexagon, right? So we know the B1, B2, B3, we have 6 points, right? So we have 6 points, but we have how many segments? See, we have 1 segment, 2, 3, 4, 5. So we want to put 6 points into the 5 segment. It means, right? Normally there is a 1 if there is a 1 point for each segment, but there must be a point within the same segment, right? If 2 points within the same segment, right, you can see there is no point here, right? Because if you draw the chord of this and draw the chord of this, there is no intersections, right? So the most one we can see is here is we have the this one, right? We can say B1, B2 will intersect the A1, A2 and the A2, A3, right? So we have the 2 points times only 5 segments, right? Because only 5 segments can cross each segment. There is 1 segment in here, so there is 5, right? Okay, so let's think about C1, C2, and AIA plus 1, right? So see when you put 7 points on 5 segments, right, evenly. So there are 2 segments will be within A1, A2, 2 points here, 2 points here, right? And then so you have another only 5 chord can intersect with A1, A2, A2, A3. So that's 2 times this 5, right? Okay, the same reasoning, right? The 2 segment between B1, B2 up to B6, right? 7 point put into the 6 segment. So there is 1 segment has 2 points. There is no segment over there, so that's 2 times 6. Okay, so based the same reasoning, right? You can see this one is 2 times 5, 2 times 6, and 2 times 7. Now let's counting all the intersections, right? 10, this is 10 and 12 is 22, and this is 10 and 12 and 14, this is 36. So the total will be 68, okay? So the answer is E. Okay, so let me recap it. Okay, so you cannot draw all the pentagons here or the hexagon because that makes the graph very messy. Okay, what you need to do is based on one single chord. Okay, you can see what happens here, and you can see there is a one segment within within A1, A5, so there is no intersection over there. So you use this way to systematically counting what happen, how many intersections. Okay, good. Now, next question. So a cube is constructed on 4 white. So we have 4 white and 4 blue unit. Okay, and the unit cubes. So the cube will be like this, right? So I draw the center of the cube, right? So this is the center. So we have this one, each point will be a cube, right? So there are 8 cubes. There are 4 white and 4 blue. And they're constructed 2 times 2 times 2 cubes using the smaller cubes. The two constructions are considered the same if they can be rotated. Okay, whenever they see the rotated, there is a rotation symmetry. Okay, when you say the rotation symmetry, I hope, you guys can know something about Burnstein lemma. Okay, this Burnstein lemma is very powerful to count, okay, to remove the duplications. Okay, so basically what does it mean is it means, for example, we have n ways of the coloring. Okay, and we have some symmetry, right? We can rotate it. We have G type of the symmetry, or we call the operators. Okay, then for example, if one coloring is here, the other coloring is here, the other color here, the other color is here, right? So you can put the rotation. You can use some rotation from this one become this one, become this one, become this one. It's like all the 4 colorings can be rotated to get each other. Okay, this is called orbit. Okay, so you can see if we want to remove the rotation duplication, basically we are counting of the number of orbits. Okay, so the Burnstein lemma basically tells us, okay, for each element here, okay, And there are some operators, okay? For example, this operator 1 and operator 2, okay? Based on the operator 1 and the operator 2, this point will come back to itself. This point will come back to itself, okay? This is called a stabilizer. So we are counting the number of stabilizer within a whole orbit. The one tells the Bernstein lemma basically tells us, okay, so if the stabilizer here is, for example, is xx1, this is sx2, sx3, sx4. Okay, I just used 4 as example. It tells us all the stabilizer on the one orbit. Okay, the stabilizer sxi. So xi belong to the orbit j will be a constant number, will be g, right? So now what you can see, if you can list of all the possible elements, right? And you can find the number of stabilizer, sx1, SXM. Then you add all of them, right? You know every G is orbit. Every G is orbit. So it must be a number times the of the G, right? Then you divide by G, you can know the number of orbit. Because all the orbit already remove all the rotation, remove the rotation duplications, right? So this is how we count it, okay? Now let me move on to counting. We need now next I need to introduce, let's see how many symmetry lines of a cube, then we can do it, okay? So for a cube, okay, I think it's very easy you guys to forget some symmetry lines, okay? The easiest way you can see is here. That's 1x, y, okay, and a z. Okay, I call this R1, R2, R3. Okay, so we have an identity, means I don't rotating this figure, right? So we have the R1, we have the R2, we have the R3, right? That's the first segment of the rotation. Okay, because they are similar, right? So for the R1 along this side, I can rotate in 90 degrees. I call R1 90 degrees. And R1 can also rotate in 180, right? R1 180. And R1 can also rotate in negative 90, right? It's R1 270. So this is the same thing, okay? You can do this. So there are kind of 9 operations here, right? 3 for the R1, 3 for the R2, 3 for the R3. They are the similar, okay? So the next rotation, okay, the next symmetry rotation will be along this line, the diagonal, okay? Let me draw it here, okay? I don't want to, I want to give you guys a clear picture. Okay, so the second rotation is along this line, okay? We have how many? We have that we call it R4. We have 1, 2, 3, and 4, right? It's called R4, R5, R6, and R7, right? Okay, so let's see this rotation, right? Basically, if you rotate it on this point, and this point, and this point, they're changing, right? This is the equilateral triangles. So the center of the equilateral triangle is rotating like 120 degrees, right? So R4 120 and R4 240. Okay, so you can see the R5 is the same thing. R6 same thing. R7 is same thing. Okay, so now let's counting the last one. Okay, the last symmetry. Okay, the last type of the symmetry will be along the center of the opposite sides, okay? Like here. Let's draw this one here, okay? And I draw this one, okay? So if we're rotating along this line, right? So this point getting to here, right? This point getting to here, Okay, so this point getting to where? You guys think getting to here, and this point getting to here, right? So it's only 180, right? Because rotating here, rotating 180 back. So that's why we have 6 such rotations. Okay, how many rotation we have? Think about it. 1, 2, 3, 4, 5, 6, right? We have 6 such rotations. So let's write down. It's R8, R9, R10, R11, R12, R13. Okay, so for each one of them, we only have one rotation, like R8 180, and the rest of them is the same, right? Now we can counting how many operator we have, right? So the number of the operator is E is 1. This group is 3 times, we have 3 rotation axis, 3 times 3, plus this is 2, right? 2 times 4, plus this is the 1 times 6. Okay, so the total will be 1 plus 9 plus 8 plus 6 is equal 26. Okay, so now we have 26 possible rotations, right? The other thing is so we know that each orbit, right? The stabilizer for each orbit sum together should be G, right? That's 26. Now we are going to counting. So how many fixed, right? On each operator, how many fixed pattern we have, right? Let's do the fix of E. Okay, I write it here. Fix of the E. You guys can think, because if I didn't move, right? So I can put, for example, red here or red here. I'm sorry, blue or white. Blue here, blue here, or blue here, right? Basically, we have 8 factorial operations, right? That's all the permutations. But think if I change, I swap all the blue ones, right? It doesn't change, right? And I can swap all the white ones. It doesn't change, right? So it's this. So this number is 70. Okay, we get the first fixed E. Now we're counting the fixed R1. Okay, for fixed R1, we need to separate different countings, right? Let's say fixed R1 of 90, right? Fixed R1 of 90 means when I'm rotating along the R1 axis and it doesn't change, okay? So if this one rotating get to here, right? This one get to here, this one get to here, this one get to here. If it doesn't change the pattern after 90 degrees, right? Means this color equal this color equal this color equal this color. So these 4 colors must be same. It's a constant, right? So we either pick blue or white here. So that's why there is 2 ways to put the on the top, and there is only 1 way to put on the bottom, right? That's 2. And it's the same thing for the R of the 270 because it's a clockwise or counterclockwise, right? So it's 2 times 1 equals 2. Now let's see some tricky part of the R1 of 180, okay? If R1 of the 180, so this point getting to rotating here, this point getting to rotating here, right? And so the same thing, this point here, this point here. So basically we divide the 8 points into 4 pairs, right? So we need the 4 pairs is the same. So we have the BB, BB, WW, WW. This one we need to assign these 4 pairs, right? So there is a 4 factorial ways. But if we swap one BB pair with another BB pair, it's the same, right? So that's why we need to divide 2 factorial by the 2 factorial, okay? That is, this one tells us it's for 12, it's 6, okay? So that's why we can get is 6. Okay, now let's see this one added together, right? Because we want use R1 for the R2, R3 as well. So this is 10. Okay, so that means okay, let me write something here. Okay, so that means we have the 70 here, right? We have this is 10 times we have 3x's is 30, right? Okay, so next let's count in what? Next let's count in the other one. Okay, let's count in the R 120 degrees, right? Okay, so the 120 degrees, right, means this one rotating to here, right? And this one rotating to here, right? Okay, so if that means we need to group this one, this three should be a group, right? So we either have the BBB, WWW, right? That's this three and this three, right? Okay, so this three and that three. Let's see, fix of the R 1, 2, 3, R4. Okay, then fix of the R4 is 120 equals. Okay, so R4 120. So we have to assign this one, right? There are two ways to assign this one. Then the other three, there is only one way to assign this one. But we have another. We have one white and one blue left, right? So one has the 2, the other has the 1. That's the 4. Okay, then are 240 over 4, right? So 240 is the same thing, right? You still need this one to be the same and the other to be the same, right? So it's the 2 times 1 times 2 times 1 is 4. So this is 8. Okay, so that's 8. So we have 8 times how many? 4. We have 8 times 4 is 32. Okay. Okay, so let's talk about the last one. Okay, the last one only have the 180, right? Let's see the 180. Okay, 180. So this one gets to here, this one gets to here, this one here, and this one here. Basically, we also divide here into 4 pairs, right? So it's the same thing. So we have the fix 4, 5, 6, 7. Okay, that's 8. R8 equals fix of the R8 180. We have the 4 pairs, right? The 4 pairs, that's 2 and 2, because when we swap between them, it doesn't change, right? So this one is 6. Okay, so now it's this one is 6 times 6, right? Hold on. Hmm? Okay. 6 times 6 is 36. Okay, now let's add all of them together. So we have the 70 plus the 30 plus 32 plus 36 is equal to 168, right? That's the total of the fix, okay? But we know this is total stabilizer, right? So the total stabilizer, every orbit, the stabilizer is 24, right? So number of orbit is equal to the fix over the number of operator. Is 168 over 24 is 7, right? So this is how we get 7, okay? So yeah, if you guys, want to really deeply understanding how the Burnside lemma work or how we do it, you can just refer to the Dr. Osman's lectures on the YouTube. Okay. Next one. Okay, so the problem is 21. It is the px equals this, and so we have the how many solutions can be the px equals 0. Okay, whenever I see this format, okay, you can see it is the it's always remind you, right? It's a film EIX, right? This is the definition. So I always like like the power because the sine and the cosine are very nonlinear. And if we can use the power of the exponential, it's much easier to handle this. So now let's rewrite it. Okay, px equal 1 plus EIX minus EI2x plus EI3x. Okay, so let's see the ratio. This one and this one, the ratio is negative EIX. This one to this one, the ratio is negative EIX, right? In order to have the EIX, what do? I need a negative one, right? And I put a 2 here. So now I can use the geometry sequence, the sum of the geometry sequence, right? I can plus the negative 1 plus the EIX minus the EI2x plus the EI3x. Okay, so now let's simplify it. Okay, so it's 2 plus, because it's negative EIX, 1 minus r, right? So it's 1 plus EIX, right? And will be negative 1 and 1 minus the negative 1 minus the negative EIX of the 4, right? So it will equal 2 plus 1 plus EIX, okay? And 1 plus the EIX, and then it will be the EI4X minus 1, right? Let's further simplify it. It will be 1 plus EIX. Then it's the EI4X plus the 2EIX plus 2 minus 1 plus 1 equals 0. Okay, so this is mean the PX equals 0, right? Okay, so we have casework here, right? Let's draw something. Okay, so we have casework. So the case 1, let's see, because the denominator cannot be with 0, right? Because originally, see, the original problem, you don't have the denominator, right? So we need to exclude that, okay? So if the denominator is 0, x equals 0, means x equals pi, right? Because we need the x is greater or equal than 0 and less than 2 pi, right? So if x equals pi, let's see what's going on, okay? So the px is equal to 1 plus ei pi minus ei2 pi plus ei3 pi is equal to 1 minus 1 minus 1 minus 1 is equal to negative 2 doesn't equal 0. So we guarantee the ei pi is not the solution, right? So now we guarantee the denominator here. The denominator is not 0, right? Now we only want the numerator is 0, right? So here, if you want to see the ei4x plus 2eix plus 1 equals 0, we can split into two equations, right? It's cosine 4x plus the 2 times cosine x plus 1 equals 0. The second one is sine of the 4x plus 2 of the sine x equals 0, right? So this one you can see we have I mean, one, right? And this one is more homogenetic, right? It's easy, more friendly to solve. Now let's solve this is the 1 and this is the 2, right? So now let's solve the 2 first, okay? The 2 can tell us it's 2 of the sine of the 2x, the cosine 2x plus 2 of the sine of x equals 0. It tells us, right, is 2 of the sine x of cosine x and cosine 2x plus sine x is equal 0. And it also let us know is sine x and 2 of the cosine, right? Let's use the trigonometry. Okay, cosine x plus cosine 3x plus 1 equals 0. Okay, so now we can have another casework, right? So the small little case is case 2.1 is sine x equals 0. So the x will equal 0, right? Because x equal pi doesn't work, right? So if x equals 0, then the px equal 1 plus ei0 minus ei0 plus ei0 is equal to the 1 plus 1 equals 2 is not 0, so it doesn't work. So the other possibility is cosine x plus cosine 3x plus 1 equals 0. And this one, if you know the triple angle formula, right, is the 4 of the cosine cube of x minus 3 of cosine x plus 1, okay, equals 0. And if you analyze the derivative of this, you can see there is a solution, okay. But the goal here is we don't need we know we want to see whether it is possible to of this solution can possibly also satisfy the first one, right? So now let's do another one. Okay, so you can see normally we always using cosine alpha square plus sine square alpha equals 1. Okay, we always want to apply this. So let's see, we have a constraint here. Okay, if we use this constraint, thus we can satisfy the constraint number 1, right? So let's using the number 1. I like to do this. For x equal to negative, it's 1 plus 2, negative 1 plus 2 cosine x. I use the sine for x is equal to negative 2 of sine 2x. Okay, this from the 2. Okay, so this is the 3 and this is the 4. Let's using the 3 square plus the 4 square. Okay, now you can see this is the 1 equal, here is the 4, right, plus 1, right, and then you can plus 4 of the cosine 4x, right? So now if you cancel, you can get 4 plus 4 of the cosine x equals 0. Which one can it make it possible, right? Only x equals pi. But x equals pi cannot be the solution, right? So now we can see there is no solution here, right? Because everything, if you want to satisfy the second equation, you can now get the first one. So the answer will be A, okay? So yeah, that's for the first 3, and I will do more videos for the next 4. Okay, thank you so much. Bye bye.